Hello, Pradeep KR. I'll try whatever the post contest discussion that I do in general. Okay. I'll go for easy ones. Easier, better for me, right? Easier or better, right? I'll try to do all because it's a post contest discussion, right? I'll do what I can. Okay. 1 minute. I'll just check. Okay, guys. We need subscribers. So whoever new people is going to watch this, do subscribe. We'll make it 1,000 subscribers in this stream. Make it 1,000 subscribers. It's 979. Is it back? Is it back to normal? I get it. See, it's due to weather. It's due to weather. Okay. So what problem should I go first? We only have A, B, C, D, E. Right. Let me read both B and C. I don't know how many stalls they have, but let me try reading both B, C, D. Okay. Let me try reading both all of B, C, D, and then we'll decide what we can or what we can do. Oops. If I close that, what's up? Nah. How good or bad is it now? Can you guys help me? Will it be fine after this? Will it be fine after this? So, was the mistake? Was the mistake Chrome's? Like the video, guys. Mm, so yeah, so yeah, so let's try to go back to AtCoder, JP, right? You guys can see my screen, right? Let me know on WhatsApp if something goes wrong. I'll try to keep that uh, here too. So let me read all the problems first. Let me read A, B, C, D, E because reading problems is important, right? So let me read A, B, C, D, E. I'll first read C. Okay. There are n people on a number line. I will read everything first and then I'll try to solve them. Okay. Let's read the problems first. There are n people on a number line. Person I is initially at coordinate Si and wants to eventually move to coordinate Ti. It is guaranteed that S1, S2 up to so on Sn, comma T1, T2 up to so on Tn are all distinct. Okay. All are distinct. He wants to go from here to here. That's what everyone want to do. You fix one permutation and perform n operations in order. In the ith operation, you move person pi to coordinate SPI to along the shortest path on the number line. However, if there is another person on the movement path, a fight occurs. Determine if there exists a permutation P such that no fight occurs. If it exists, find one. So this seems a good problem. You have to use logic. You have to use logic that okay, if everyone are going from here to here, is there an ordering where everyone can go and no one face a fight? It's a clear and good problem. So you have to use logic to connect these things that okay, n people are there, everyone are going from here to there. What are the necessary and sufficient conditions that says that it exists? And if it exists, you have to find one. So the problem is like you need some work, you have to logically try to find necessary and sufficient condition for no fight existing. For the existence of a permutation, you can find necessary and sufficient conditions. Okay, because if it doesn't exist, then if it exists, you also have to print that permutation. Okay, output. Or else you have to say no. So this is a good problem. You can try to find necessary conditions in the worst case, right? Now let me read B. Uh, were people able to read C? Hey, like the video, reply to chat, be active. You're getting premium content here. Okay. Yeah, and people want to go from SI to NI. And is there a permutation where no one fights anyone else? Okay, that's the problem. Seems simple, but what I mean is it's about finding those necessary and sufficient conditions so that what does the existence of permutation means because you cannot have n factorial in your code, right? So you have to find those necessary conditions and sufficient necessary and sufficient ones. Yeah. So let me read B. There is a complete graph with n vertices numbered from 1 to n. Each edge is colored black or white. For I equals to 1 to m, the edge, complete graph. Complete graph means nc2 vertices. For I equals to, sorry, nc2 edges. Each of them is black or white. For I equals to 1 to up to so m, the edge connecting the vertices ui and vi are colored black and other edges are colored white. So we know the less number of edges that are colored white. Black. We have lesser number of blacks probably. We cannot say entirely less, but black has a bound to E5. White edges can go till here. I don't mean black or less. Okay. We can perform the following operation 0 or more times. Choose a triplet of integers A, B, C such that and repaint each of the three colors white to black, black to white. So we flip three things. Probably a nice problem, right? We flip them. Find the maximum number of edges. Nice problem again. So I have taught you people some things in the past, right? First thing, is this operation reversible? Yeah, it is. That means we can form equivalence classes on here, right? We can form equivalence classes. I mean, you can go from this set of edges being in black to this set of edges being in black. So this operation is reversible. Those few things we can use directly here. So let me try to solve this to a bit. Okay, operation is reversible, and we have to find maximum number of black edges that are possible. So if the operations are reversible, that means it forms an equivalence class, right? So now you have to find, okay, in this equivalence class, what is the maximum number of black edges you can achieve, is what you have to find, right? So let's say more about operation. What doesn't change here? What doesn't change? Because whenever there are operations, looking for invariance is a good thing. I have told this in the past too. So all problems are same type. If you're not solving, you're not paying enough attention when you solve a problem. Okay. So now let's just see here. If black changes to red and red, so it's like, I think we can just say a few things easily, right? Mm, what doesn't change? You're taking three things, right? You're taking three things, and things change in them. So three things change, right? So what changes or what doesn't change? We have to see a bit, okay? What is an operation? AB, BC, CA flips edges. So what doesn't change here? What changes or what doesn't change? If you're only allowed to do this, what doesn't change or what changes? If you look at one vertex A, so two of its edges are changing, right? Two of its edges are changing. So if you try to keep, uh let's say, see, plus one and minus one type of thing, right? It is like, let's say, uh I represent white edges with plus one, minus one, and sorry, plus one, and black edges with minus one. Okay, if I just represent them like this, what happens to this set? It's just that white may become minus one, black may become plus one now. That doesn't change. What am I trying to show here? No, I thought of saying something, but then two things will flip, right? So what happens after an operation if two things will flip? If two things will flip, if two things will flip, let's see. If plus one comma plus one got flipped, we have minus one comma minus one. If plus one comma minus one got flipped, we have minus one comma plus one. If minus one comma minus one got flipped, we have plus one comma plus one. So currently we are not even seeing three things at a time. We are only trying to see what happens to A. And that says parity of parity of number of plus one edges doesn't change. Parity of number of minus one edges doesn't change. These are necessary conditions, right? Why? See here you have two plus ones. Now plus ones count became minus 2, minus ones count became plus 2. That means that parity doesn't change, right? Parity of minus plus ones didn't change, parity of minus ones didn't change. Even here, everything remained the same. Count itself remains the same. Leave parity aside. Here, parity doesn't change again. So these are like some necessary conditions. After an operations, these things doesn't change. But just if the parity doesn't change, is that enough? Is the second question, right? Can you form all such things where just the parity doesn't change, but see, you can say some things like, okay, these things doesn't change, but just if this doesn't change, can you achieve all those possible configurations which satisfy these conditions is another question, right? Maybe not. Then maybe you need more. What all the operation allows you, we have to find. I didn't even wash face today, so I think I need polo. Damn you. Yeah. So is it working? Bro, what do you mean reversible wasn't the case? Do we have reverse? So if you see those things, are these necessary is one thing we can think of, but let's try to see if you can say anything else too, okay? I think this seems enough. Why? Maybe this is enough. Another observation. This is another observation, right? Just a small observation. If you can flip, if you can flip ABC, that means we can flip any cycle, right? A, B, C. Instead of that, flip C1, flip C2. But then, I mean CD. But then how do you flip these things? You flip these things first and then you flip these things next so that everything is flipped. So this is an observation you have to make again. Because any polygon or any cycle can be split into these things, right? So you can flip. So you can flip any cycle. You can flip any cycle. So what does this means? And if you can flip any cycle, you can flip any length cycle edges. But then probably this is enough. That means probably this is enough. If the parity remains true, maybe that's enough. Probably. So let's try to see very clearly. So now we have total number of edges on each vertex is n minus 1. number of black edges is b b of v. Okay, so if both b of v comma w of v is odd, you must have, we want maximum black, right? Let's see if this is possible. Let's see if this is possible. Let's say this is possible. If w of I is odd, we must have an white edge finally, right? And how many times w of v can be odd? Sum of all w of v's is even, right? Sum of all w's of v is even, right? Because a white edge will be counted once here and somewhere else there. So so can we just pair these odd white vertices and make everything else black? But if this is answer, this is too simple of a problem, right? All the problem demands you is this, trying to find some small observation on that operation. You should also be able to find this. But maybe this is the answer. But then if this is the answer, because proofs are simple, we can probably prove it easily. Okay. If this is the answer, how can I prove it if this is the answer? So let's say let's try to use induction a bit. It's unnecessary maybe induction, but let's keep one vertex aside and everything else you were able to make them as, because it's a complete graph, you were able to make them as all black. Only odd white edges have been connected. Okay, so let's try to prove using induction. See, if you make a good claim, checking its proof is not very difficult, and you should try to do that. Okay, let me try to use induction. So now you have one vertex here. I'm trying to use induction on number of vertices because edges are too many, right? But number of, so now this is a complete graph, and you can convert this into, let this be white. You can convert this into white pairings. Everything else is black. This is our claim. And and now what happens? All the black edges. Okay, now we have some sorry, we have some vertices which are not in any pairing. We have some vertices which are not in any pairing. We have some vertices which are connected by green edge, right? We have some vertices which are connected by green edge, right? So now we are having edges from this. Let's say there are zero black edges, zero white edges. Then, or even number of white edges. Any white edge you take here, okay? Any white edge you take here will change parity of one thing here. Let me see a bit more. Okay. So what we have to prove? Uh, so any white edge you have to this, let's say this is the additional white edge we got. So now this parity has been changed, this parity has been changed, and both of them are odd, and then we have connected them. So this is true for one white edge. For one white edge from here to here, it's true. Let's try to see for two white edges if this can be true. Okay, for two white edges, this can be made even, and maybe you can add green edge here and then both of them will be black. Seems working. Even if it is three black edges, if you add one more edge, you can still make it. Do you get what I mean? So among these things, whenever you have a green edge, that changes parity of these two things, and then you can probably. So what I mean is, for all the edges that are green from here to here, if this is green, it's already satisfied, right? Okay, and then you add one more edge, let's say. So we can even prove this using induction on number of green edges too. I think because if you add a new edge, so let's say everything is like this. Everything is like this. Okay, everything is like this. I think whenever you add a green edge, additional green edge, you can probably prove it well. Like maybe instead of these two, just make this green. So it seems true. So let's just submit this. Let's not think too much. I cannot shout much. Parity of white edges, right, is what we want. Parity of white edges, right. If it is wrong, I will go back to my proof and then maybe find some more things. But I complicated proof. There can be more simpler ones. At least without proving very well, very formally, we can try to see it somehow. We can try to see it somehow. Okay. How can we try to see it? How can we try to see it? Let's try to make better proofs. Let's try to make better proofs. What does it mean that you don't have all greens getting paid well? What does that mean? That means some odd vertex is having more than one thing, right? Some odd vertex is having more than one thing. Okay, let's say that's the case. Some odd vertex is having more than one green things. What you can do? Flip this triangle. Number of white edges reduced by one. Better proof. Induction. I felt it's complex, but we have simple proofs as per golden rules. So, what does this say? I don't want more than one green edge on an odd vertex. So whenever there is an odd vertex, you can flip this triangle and the number of green edges reduced. You can do this further. As long as there are green edges, you can reduce number of green edges. So this is a perfect proof. You can always pair them. So I'm done. On any vertex, not just odd, even on even vertex, if there are more than two green edges, you can reduce number of green edges count. So you can finally come here. So this is perfect proof. This is a clear proof, right? So proofs are simple. Again, I am showing you people how they are simple. This is premium content. I'm shouting from the top of my throat, and we don't have viewers. See, it comes from seeing invariant. I have told you people already that you have to see invariant, you have to see if the operation is reversible. Right. I have told in some video that we have to see invariant wearing the same t-shirt. Same t-shirt, same content, but we never learn somehow. Not same content, it's good content. Okay. Because who other CP, you guys don't want good mathematical logical content. You guys want some shitty LinkedIn post that says, oh, see, today I have done this, today I have found this, today I learned that. You guys want those things. You guys don't want real content. That's why, right, we have so many content creators, we have so many people saying so many things, and still people stay the same. Why? Because people don't want to change, probably. So just seeing this invariant is was enough. Many people might not have made this beautiful proof that I made, that you can always reduce number of green edges. Because see, what do we want? We want number of green edges to be less than 2 finally. Even vertices should have 0 green edges, odd vertices should have 1 green edge. That's what we want. So just take the contradiction, not the contradiction, just take the contrapositive. Is that what it is called? I think it's contrapositive. Just take the contrapositive. Okay, if there are two things, prove a contradiction. You can reduce them further, right? Or proof by contradiction. Okay, in the optimal, in the minimum number of green edges, if there were these things, you can reduce further. That means these things doesn't exist at all in the minimum. Done. Simple proof. So this is obviously a correct solution now. All I care is parity, right? Now I will count. So this is parity of black edges, right? This is parity of black edges. But then what's parity of white edges? White edges is nothing but n minus 1 remainder 2. This is total number of edges. With that, I am trying to see parity of black edges. So XOR of total and or black will give us white, right? So we are done. And this will be even for sure. So only these are the white edges that remain. Everything else is black. So this is the answer. Okay. See, even if I overcomplicate an easy problem, still it's good content. Okay. Am I even happy for this problem? I mean, if it was having a bit more complex things, then I would be happier. Why can't I submit it? So just finding one simple invariant, the problem is solved. Just this invariant was enough. Just look at one vertex. Things are looking complex, but just I'll just look at one vertex and see what's happening with that. With that, this is what's happening. Right. If you look at number of white edges, their parity doesn't change because two edges got flipped. Two edges got flipped on. One thing is the only thing that's being used here. Parity of white edges doesn't change. You want minimum number of white edges. If parity doesn't change, okay, on this vertex a white will remain, right? Then okay, maybe what's the minimum is finding all these white odd edges. It's so being so obvious. If you believe in golden rules, if you try random things without thinking, okay, solution is simple, okay, proofs are simple. If you don't believe in that, then you will try random things. Okay, what random things can I do without actually solving the problem? That's why I emphasize why golden rules are important, and still you guys cannot get that. So let me read A. Okay. Or should I try reading? Should I try C some more time? Let me read D. Hi, Yash Mohta. I know that. I'm not disappointed. I know if I cover AtCoder, maybe I'll get new viewers, right? So let's see. I know we can go 1,000 right now, but let's see. Let's see by the video. So where am I? So we have solved B. So we have done good in B, right? So let me read A and then D. I won't solve A. I don't want to disappoint people by trying to do A. I will read A and then I'll go to D. Okay. There is a grid with n rows and n columns. Let R comma C denote the cell at the rth row from the top and cth column from the left. Each cell is colored black or white. It's all black and white. Black uh, text, white background. Cell R comma C is colored black where? Okay, you're given Q questions about this grid. So answer each of them. In the ith question, integers ui, di, li, ri are given. So find the answer to the following question. So in the ith integer, we have four things: up, down, left, right. It seems. After coloring all the cells that do not satisfy, just leaving out this small block, black. Find the maximum number of times you can perform the following operations. So what do they mean? After leaving this out and then performing, making everything black, then you have to answer. Choose a pair of integers r comma c such that r comma c plus 1, r plus 1 comma c, or okay, a small square over there, are all colored white, and color one of these four vertices, but one of these four cells black. I think covering this to black is the best thing, right? Or this. Solve each question independently. In other words, the color of each cell is reset to initial state after each question. Okay. First step, how do you solve? Because you can leave about other things getting black. First step, solve when you're given a black comma thing, like when ui equals to 1, di equals to n, this is being n comma, everything is 1 comma n. Then how do you solve the problem is the first step, right? You have to just think of that first, because that must be solved, right? If all of them are 1 comma n, then that must be solved. So first you have to think of that problem. Okay, I won't solve it entirely, but yeah. So given a matrix, what's how many operations you can perform, right? I think greedy will work. Like if we look at top left, topmost and leftmost white vertex that satisfies this property, then you can color it black. And this doesn't change So if this satisfies, you can color this black. And then if this is being the top left, also if this satisfies, you can color that later, probably, right? Because you're only coloring this. So if you're coming from top left, you can color all the cells for all the 4 cross 4 cells. For all such R comma C, you can color all of them. There is no any restriction here, right? If you're trying to come from top left, if you're trying to come from top left, you can color all. You can color all cells that's R comma C such that the 2 cross 2 square formed by it is white. So we just have to count now number of 2 cross 2 squares that have been colored here, right? That's what we have to count now. So so where are we? So now we have to think of the other problem. Okay. Counting this is easy. Right? Counting this is easy. But if you have to count that for this subarray, for this subgrid, then you have to be careful about the points that lie here and that lie here. You have to subtract them because for every other point, the whole grid exists inside. But for these white vertices, for these four white vertices, they are going out. Total number of white cells this grid, and you're done. If you have to count this grid you're done. In this grid you have to count all the cells, right? Subarray, you maintain solve this problem, but then because it's so fucking easy, I'll just write the code very quick. Okay, I'll maintain fixed subarray, right? We want white. Let me just take the array. No, I will update the array. So this is one, right? So now I will change the whole array from top left again to, we have to be careful here, like if you are not changing arrays in the wrong way. Okay, So we are changing all of them into what we want. Now I'll find prefix arrays. So all rows are now prefix arrays. Now we want all columns. If you prefix columns now, that works. It's J of I now. If n and m are different, we have to do it like separately. But because n comma m is same, I'm just using it like this. Okay. Now what's the answer? So down minus minus, right minus minus, and then for this subarray, I want the answer. For this subarray, I want the answer. Number of ones inside this. Number of ones inside this is what I want, right? I will also do L minus minus R minus minus for for my convenience. Why? Sorry, L U minus minus for my convenience, because now we have prefix array endpoints, right? Endpoints are a bit important now. So we know now what to do. Pref of down right minus pref of down left minus pref of up left, up right maybe, plus pref of down up left. I'll just see if the prefix arrays looks good or not. Okay. I'm wasting time on this problem, but let's see. How can this be 9 and this be 6? Doesn't make any sense. Right. Now for all columns, we are adding up rows. For all rows, you're adding up columns. For all columns, you're adding up rows. Let's see if we are doing this right. Should I have been careful somewhere? Is this correct? One, one. What are these two ones? These two ones should be wrong. We last rows are redundant anyway, right? So now this is perfect. If this is perfect, why the fuck is this getting fucked up? How do we have three things here? Why am I not able to just prefix them perfectly? Yeah, we should not do such shit. We should do them separately. Now for all columns, because you're affecting that. I faced this long back. So also this is so. So let's try to go for C, read D, and then come back to C. Okay. Maybe those are like a bit good problems. Yes. Yeah, this seems better, right? So, so far what we have done is we have solved uh, So far what we have done is we have solved B, we have solved A, and for A my screen has gone for some time. So let me try to show what I was doing was I was trying to debug. I was trying to debug. After debugging, the error was I kept this loop inside, but that seems to be wrong. First we have to make these things and then we have to make these things. First we have to add up column rows and then you have to add up columns. Okay. Because if you add row and then you add column and then you're adding this to this, that's wrong, right? And then this got solved like this. Trying to take the whole rectangle, subtract this rectangle. You have this thing. Now you have a way to get this thing. So follow that way to subtract this and this. You have this. It's like that. It's like cutting it. You can try to say it in any way possible. Okay. This thing you can try to see it in any way possible. You can try to see it like this minus this. See, this is like to get to get. So now how to submit. So this is my phone hotspot. This seems to be working fine, right? It keeps increasing. So this seems right. This seems fine. I'm using Wi-Fi again. So guys, we have read C, right? C says, so we have read C. C says, is there a way you can go from T1 and not interact with anything else, right? Hope it works. So let's try to focus on first element. Can we try to say something on the first element? Okay, because then maybe we can proceed inductively, right? So let's try to focus on first element for a while. P1, right? What does P1 satisfy? Can P SP1 to T, it's S to T without having anything in between. I think my camera quality has improved after I rub it with the scarf, I think. Okay. So now I hope it works. So I'm trying to see what about the P1? For P1, what should happen? For P1, what are the necessary conditions? From S to T, this is one necessary condition. Means there is no S ice in between. So this is one necessary conditions. For P1, there should not be any starting positions in between because that should be happening, right? And once you have gone there, once you have gone there, what can you say? Once you have gone there, what can you say? There should be no. So, so once you have gone there, for T1, TP1, there should be no S to T on it. Right. So even for so so this is it, right? So for TP1, there should be no S to T on it, right? So this says something. There should be no S to T on it, right? So if P1 is somewhere, and there is another thing too. If these two satisfy, what does that mean? If these two satisfy, I'm just trying to look at P1 for now, okay? I'm just trying to look at P1. What can we say? For P1, let's just see for P1. For P1, there should be nothing SS in between. No SS in between. Means starts can some be here, starts can be somewhere here. If I try to make end as red, there are no green in between. Okay. And after that, for this we have a bit more condition that nothing falls on top of it. That's another condition. So nothing falls on top of it. Nothing falls on top of it. So they're either totally this side or they're totally on this side. But then what happens? Nothing starts in between. Means people can start here, but then they will be here. So this is allowed. But nothing starts in between. All such things are valid for P1. Right. If these things are same for everything else too. For pi, everything from I plus 1, I plus 2 up to so on, they cannot fall over that. They have to fall. Okay. What can we do greedily? This is probably greedy, right? Or let's try to see. Let's try to say what we can say first. Okay. It seems intersections, but for P1, what can we say? What are all the possible candidates for P1? That can be a question, right? What are all the possible candidates for P1? So, what are all the possible candidates for P1? Nothing should be crossing this T. How many such T's can exist? Many, right? Okay. Now let's look at all those T's. All those T's where all those T's where nothing crosses that. Okay. If if so nothing crosses this T at all. Nothing crosses those T at all. We're looking at all those T's. Now, if if among all those T's, maybe among all those T's, how will they exist? Maybe you will have such a T here too. Right? You cannot have such a T in between these things. Why? 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 Because you cannot have that thing in between here. Why? Because nothing crosses the T, right? So if you look at things, it, then T is where nothing crosses it. then that won't be here. That will be again somewhere here. Okay. Now we have many such T's. Nothing crosses it. Okay. But we have to see among all these things if there is one T without any SIs, right? Among all these possibilities where nothing crosses it, we can even say this thing. If something crosses that, that should occur before that. We can also say that. Okay. If something crosses that, that should occur before that. But let's look at these things. Okay. And let's say we found a valid thing where nothing crosses this and no start things exist in between. No start things exist in between. Means if you have found at least one such a thing, okay, no starts in between, nothing crosses it. Doing this now, is that beneficial? I don't know what to say that. What to say to that? My maths is kind of poor. So so if you look at necessary conditions of that, okay, nothing crosses this T, okay, nothing crosses that, and nothing starts in between two. If nothing crosses that and nothing starts in between, why not just do that right now? Why not just do that right now? So this necessary conditions of P1 seems enough. If you guys notice that, I have to do streams on how to get muscles, how to get. I should do all those streams, I guess. It's not visible. We need lighting. Now, we have to solve problems, bro. We have to solve problems. Uh, I think that will sell more because people are horny all the time, right? That will sell more than this coding. Nice, bro. What is Jeff Nippard? I don't know, but yeah. So, guys, see how looking at P1 is just solving the problem. P1 necessary conditions. What? What? Nothing crosses the end point, right? Because if something crosses the end point, wait, 1 minute. Some things can cross the endpoint totally, but then so for P1, what is allowed? For P1, what is allowed? For P1, these two conditions, right? Going from here to here, nothing, no SSR here in between. That's one condition. And after that, okay, this is also not allowed. Even this is not allowed. Yeah, that's true because after you do that, it stays here, right? Then That's also not allowed. So for P1, if nothing crosses it, nothing crosses, and there are some things in between, but nothing starts in between. So if nothing crosses it is a must condition. If nothing crosses T and nothing crosses that at all, right? If nothing crosses that, maybe there are few things over here too. Okay. If nothing crosses that and no starts in between, that means no starts in between. Doing that in the first itself seems best to do, right? Because anyway, nothing will cross this. So, if you are doing this, friend, maybe you will save other things, right? You will save other things. So, so P1's, so P1's necessary conditions are sufficient enough to make P1 as a greedy move. It's always good. It's always good to do P1. If something is a valid candidate for P1, it's good to do. Okay. If something is a valid candidate for P1, it's just good to do. So now we have a solution. Maybe in n square complexity. You can try valid P1, do that. And then now find valid P2 and then do that. And then find valid P3 and then do that. So now this seems okay. Necessary conditions of P1. What are necessary conditions of P1? For TP1, nothing else should cross that. From S to T, there should be nothing in between. No S should be in between because SS would not, right? From S to T, no SS should be in between. For SS, no SS should be here. And it's like inverse somehow, right? So this should not be on any SI, nothing should be on this TI. This should not be on any SI, nothing should be on this TI. Those are the conditions. This should not be on any SI, and that should not be on, and nothing should be on top of that. If nothing else on top of that, okay, we can visualize that. This should not be on any SIs. If you take lost TI, nothing cannot be on top of that, right? If you take lost TI, nothing can be on top of that. But we can have SIs in between, right? But if you take lost TI, we can have SIs in between. So now let's look at inside this thing. How complex can things be inside this thing? Again, let's look at lost TI inside this thing. Nothing can be on top of this. But some things can be on top of here. Again, let's go inside. And then again, let's look at the last TI. Again, something can be on inside. If you keep going, we will have a TI where nothing is on top of it, right? Where nothing is on top of it. So the conditions, maybe Maybe would this work? But how do we give not right? I'm just trying to see if there is a better way to find that uh, P1 or T1. Is my previous thing correct? Okay, go to the last T because nothing will be on top of it. Now, now, see inside this. Inside there are some SIs because if this is failing, inside some SIs. Now I can go among them last T. Okay. Again now inside that if you go to last T, among these SIs, among these SIs, among these SIs. No, but this doesn't seem right. This doesn't seem helpful because some other can come cross these SIs and then can come here, right? What about so all the TS has the same crosses them is one thing we have. Even this wouldn't work much. See, one thing, if you can find this TIs itself easily, then we can proceed further. I'm just trying to see can we further simplify the process of finding these things. Okay, so nothing falls on them. So the TIs where nothing falls on them. So this is like for TIs nothing falls on them. You want TIs with only starts in between. So we are taking such a process it right. Between. Am I not able to solve this problem? If you look at last SI, if you look at last SI, maybe it has things right. If you look at last SI, maybe it has things on top of it. But is there anywhere where we can say when it's impossible? Let's not get stuck here. Let me read D2. Okay. You're given a rooted tree of n vertices number from 1 to n. Vertex 1 is root and the parent of vertex vi is pi. Initially, all vertices are colored white. You can perform the following operation sequence of operations more number of times. Consider a pair of integers u comma v that satisfies all the conditions. Both vertices u and v are colored white. U is not an ancestor of v. Okay, u is not an ancestor of v. U is not an ancestor of v. Maybe v is an ancestor of u, but then for all pairs where u less than v, so the pair is a bit fixed and pi is less than I, so all the ancestors are already smaller. So we want smaller things who are not ancestors. So this makes it a bit more clear because all the ancestors are already smaller. U is not an ancestor. So in the tree, we have to go to some other subtree, not to ancestors. For all such pairs, color vertices u comma v black. So both are colored white, you have to color both of them black. This is what you can do. This is what you can do. Okay. What does this mean? That's known to us. Find the maximum number of operations you can perform when you perform operations in appropriate order. So order matters here, right? Because once you make whites as black, you cannot use that white with any other thing. So how does this thing have a simple proof now? How does this thing have a simple proof? Right? Because we are finally writing a code. So we are simplifying things a lot from this complex procedure. We are simplifying it. So we have to think a bit of ways you can do that when it's not an ancestor. Initially all colored white, right? One thing I can say is you cannot do shit to one, right? You cannot even touch one, right? One obvious answer is uh, not an answer, one obvious possible thing. We have to show lower bounds too because this is a maximization problem. Maybe you have to show upper bound, that you have to show that above this is not possible. You can even think that for simple proofs, you have to show an upper bound. Not even for simple proof. If you are proving, you must show an upper bound. Uh, okay, one small possible value is there, right? One small possible value is there. This is not an upper bound. This is like lower bound. An answer. Possible lower bound is at each level, take number of things by 2. So let's say on level 1 you have root, which is 1. On level 2 you have few things. This is an obvious pairing anyone can do. And if this is the answer, it won't be here. That's for sure. Because this won't be D asking you to just try something like that. 2, 3, 4 or something. 2, 4, 5 or 3, 5, 3, 4. So something like that. So this can be an answer, right? But this is a possible answer, but we have to focus on upper bounds, or we have to show this is an upper bound. We have to show that you cannot do more than this. But how can you show that you cannot do more than this? Probably we can do more than this, right? Just let's just look at this example itself. Okay, answer says 2 pairs, but then you can take this and this. You can take this. Let's say all of these are like uh, these two come under this come under this. Let's say that. Okay, you can take these two. You can take this and this. So you're taking more. So this is not an answer. You need a better upper bound. So this is a lower bound. Lower bounds never help. All you guys try to find lower bounds. You go, okay, you can find a lower bound, and then you have to see if this is a good enough upper bound. No, if this is not an upper bound, then it's useless. Always when you guys try to find optimal, you go from other direction. That's entirely wrong, I guess. Like somehow upper bounds are important. Like what you cannot do, what you cannot do. Right? We are pairing. So n by 2 is definitely okay. One you cannot pair at all. One you cannot pair at all. Right? One you cannot pair at all. And if there is a subtree of size greater than or equals to half of remaining things or so, then maybe you can just pair that subtree with other things, right? Maybe if there is a subtree of size, okay, if there is a subtree, one you cannot pair. So remaining that, let's say you have jet things. No, upper bound. See, Yashmohita. By upper bound, what I mean is, given a tree, you have to find an upper bound for the answer. Given a tree, that's what I mean. Okay. Given a tree, you have to find an upper bound because if you're telling that this is the maximum, you're also showing that that's an upper bound. Showing that this is maximum, showing that that's an upper bound are same because you're telling you cannot go further. You're telling max plus one is impossible, right? So what I mean is by upper bound, you have to make an upper bound for the same problem is what I mean, like for the same problem. So I'm trying to write upper bounds now. Okay. Okay. I can try. I'm trying to see at one place where it's possible. Okay. At one place where it's possible. Let's say you have a subtree of size. So after one is impossible to pair. And then you have jet things, let's say. And then there is a subtree. Not even a subtree. Let's try to look at this thing. Let's say you have this subtree. From root, you have these things, and then you have this subtree. Okay. I'm trying to see if other than these things, if you have other things, we can pair all these things, right? Like from this subtree can be paired with all of other things except these things, right? So I'm just saying if there exists such a subtree, but if above things are having, then we can even pair these things too, right? But even here, if you can pair something from here and here, that's still beneficial, right? That's still beneficial. That is still beneficial. So maybe, maybe you will do that and save something else. So can we use like recursion kind of thing? Okay, you make this greedy as possible, maybe not, but let's try to think again. Okay, okay, we can show by we can even focus on okay because Ishmoto came and became number one fan already. Uh, we can even focus on trying to see some structures and maybe writing a upper bound for them. That's also good. I'm just clarifying on what my upper bound meaning was, but then we can even look at some structure and then try to say upper bound for that too. Like if you look at line graph, if you look at line graph, answer is no, right? You cannot do even you cannot even get one pair. But how do you show an upper bound for this to be zero? In terms of what can you say that upper bound like? What is limiting this to not pair anything? Everything is an ancestor of everything. That's limiting it. But okay, what if you have something here? Then you can pair these two. But then if you have something here too, then you can pair these two too. Okay, leaf. You can pair two leaves always. You can pair leaves always, right? But then, can you remove those leaves and then can you proceed further? Even that is correct. You can pair two leaves, you can remove them. But why is that correct? Why is that correct? Because, why is that correct? Because now at some iteration you're trying to remove these two leaves, okay? At some iteration you're trying to remove these two leaves. What does that mean? Below subtree has been somehow paired and got removed. So they are all good. Now these two are leaves, means they cannot be ancestors of each other. Right. They cannot be ancestors of each other. And you can remove them. I'm just trying to show you people that trying to remove leaves paired sequentially is correct. But now that is correct. The problem of pairing things can be uh, brought down to no. What we found is removing leaves forms an ideal pairing. But we haven't yet shown that like ideal pairing can always be brought down to removing leaves. That we haven't shown, right? That we haven't shown, right? So let's try to see that too. Let's say we have a pairing that has bottommost white color pairing, okay? Bottommost white color pairing. Let's say it is getting paired to this. If this is a non-leaf, if this is a non-leaf, we have some things below. And this is the bottommost thing that's getting chosen, right? So we can claim instead of this, just pair these two. We can claim that. So there is always an optimal where one endpoint is a leaf. Okay, now let's look at these optimals. Now let's look at these optimals where the bottommost point is a leaf, but the other thing is not a leaf. Okay, now again apply the same idea. Instead of that, you can move here. So that means there is an optimal where uh, two of them are leaves. That means so can we provide upper bound in terms of leaves? So what we have proven is there is a way where you can just remove leaves and form all possible optimal pairings. That's what we have proven by making that there is a leaf in optimal just by this greedy point. We have actually proven that the problem can be simplified. See, leaves form a good pairing doesn't mean all good pairings have some leaves being taken, right? We have to be very careful with logic somehow. It's about doing simple a implies b. Does that mean b implies a? It's just doing that, but it's very difficult somehow. Just being able to logically carefully do if a implies b means b implies a or not is very difficult. All problems are that, but somehow it's very difficult. See, because this could have been the optimal, right? But then I'm showing that instead of if this is the bottommost leaf, okay, and if this is also the bottommost leaf, okay, what am I showing? So I just made this statement of moving this down seems correct, but moving this seems doesn't correct because there could be in between things, right? Maybe all of them are taken. Moving that down doesn't seem that correct. because there can be leaves when you're trying to move that down. But then if you encounter something, maybe you can just switch those two, right? Probably you can switch those two because this is seems always better. Why? So what I mean is, this is being our problem. Is this worse than this? Is being our problem. Why? So now this got a lower parent, right? This thing, this thing is not a parent of this. Means I may be complicating, but let's look at that. This is not a parent of this. This is also not a parent. So if we have this that says this is not a parent of that at all. This is not a parent of any of here, which says that is in some other subtree entirely. It's nowhere here. So that is in some other subtree. But it could have been here too, right? Or here. That means if it is here, but then this will contradict. So if this exists, then this and this entirely are in different subtrees. If this is a good pairing, then all of them are in different subtrees. That's what I'm proving. So if they all of them are in different subset, then we can probably do this. Okay, then we can probably do this. So what I mean is, like, if we have something like this, then we can definitely do this. By this also you can say, by this we can very well say removing leaves is all good. By this argument, this cannot be moved down because there may be this may be taken. This argument is right, this argument is not that right, but then this argument makes things okay, everything can be moved down. By that we can maybe remove leaves. Okay, but this can be an upper bound in one way here. Let's say you have just leaves everywhere. So number of leaves by 2 is an upper bound for this problem, for this structure, right? For this structure, number of leaves by 2 is an upper bound because that's all you can take. So you can always pair leaves. So if something has more than one leaf, if some if something has more than one leaf, is it always good to pair these two? Let's say this is getting paired to something else, this is getting paired to something else. Maybe not. Maybe not. Right. They can help other things. So probably not. So we have initial leaves. Okay. We have initial leaves. Removing leaves is a good thing. Removing leaves is a good thing. We can remove any leaves. But then now, now let's look at what's left finally. What's left finally if you keep removing leaves? Because as long as there are two leaves, you can remove them, right? As long as there are two leaves, you can remove them, right? So when do you end up not being able to remove anything? When there are no leaves, when there is only one leaf, this is the case where you end up. not being able to make a move further. Ah, Pradeep K are doing better than me. Maybe if we pair the siblings, then that would be give us upper bound. So okay, but then there is one more thing, Yash, that we can see here. Maybe you're right. Maybe I'm not. I haven't thought much about what you have said. But then until here, we can keep removing leaves. We can keep removing leaves until here. So now these things we can't remove. So now we have to think. If you keep removing leaves and you end up at something, what's that? Minimizing this can be our goal now. How can you keep removing things and then end up with a straight thing that's very small? This can be a lower upper bound. This is definitely an upper. Now this is a lower bound for the reverse minimization problem. Okay, now we're trying to look at the reverse minimization problem among all possible ways of removing pairs of leaves. Pairs of leaves. Okay, as long as number of leaves greater than or equals, it's not even pairs now. As long as number of leaves greater than or equals to 2, you can remove some leaves. Right? Do two leaves. And then you end up with this stick. What's the smallest straight graph you can get? Is what we have to think now. Let me get some water. I'm shouting, right? By the time you guys can try to think a bit. Okay. So longest straight graph that will be left by only removing pairs of leaves is an upper bound, right? And if you on this upper bound very well explains the straight graph, why the answer is 0, because this is already the longest straight graph which cannot be removed, any pairs of leaves that can be removed. So among a tree, the whole tree, I hope I am able to. Minimization of the strike thing is what I mean. No, what I'm trying to say is two viewers. How many viewers do we have? As the final structure is simplified, what I mean is that that's an upper bound right now. So maybe we can brute force on all these vertices to and then see if you can remove everything else uh, as pairs. Maybe we can even do that. We want minimum this thing now, okay? Minimum straight path for which everything can be removed. That's why I told lower bound now, okay? Because we are looking at a minimization problem. Minimum straight path where everything can be removed as pairs, okay? Minimum straight path where everything can be removed as pairs. For this vertex, okay? If you try to see, maybe for this subtree, maybe for this subtree, if they can help each other, if they can help each other, and then you have a minimum length that cannot be removed by using these things, okay? So if we are looking this thing, okay, we have some below things, we have some other things, we have all these things, okay? Let's try to brute force on that thing once, because now that structure is a bit simplified. Now because that structure is a bit simplified, I don't even know if removing leaves is same. I don't know if I have proved that well, but then now because this structure has been simplified, 1 to v subtree, above thing subtree, above thing subtree, above thing subtree, above thing subtree, right? So all of them will have a leaf. All of them will have a leaf as long as they exist. Pair them, remove them. So when does the problem appear? When does the problem appear? If this is the smallest v, if this is the smallest v, if this is the smallest v, when does the problem appear? When all of them have been gone and only one thing is left now. Okay, of only one thing is left now. But then this is the smallest v that's possible. Let's assume that this is the smallest v that's possible. What can we say? Guys, anyone following me? Am I able to do that? Yeah. So let's say that. Let's say we have all these subtrees, each of them will have a leaf as long as they exist, right? We're trying to remove leaves from different things in pairs. Then we will be left with only one subtree. And even in that subtree, we will only be left with something like this, right? Guys, see how I'm using logic. Okay, because I'm using logic, I'm doing like weird things, right? So now what do I claim? Now what do I claim? Now what will I claim? If this is the minimum, if this is the minimum v actually, then this thing doesn't exist. Why? Because here we can keep removing minimum of this or this, right? We can keep removing minimum of this or this, and then you keep going further. So I claim that this is minimum. So if this has existed, that means you can remove this and this. Finally only one will be left. But what if that one was this? Then you cannot remove. Then you cannot remove. So for minimum v, where you can remove everything, and for minimum v, if that is the minimum v where you can remove everything, there is a way. There is a way. I think this is going back to the same initial problem, I guess. Like initially I tried fixing one v, trying to remove these things better, but then we haven't done much. I think I'm again coming back to the same thing somehow. Initial just intuition. Maybe that's why it's an easier problem than the logic I am applying. I don't know. uh, so what does this mean? This will not be, there is a way to pair everything and leave, because if there is no way, okay, we have proven that there is a way. If you keep removing, this will not be left. Why? Because this is optimal, this will not be left. But if this is being left, because this is optimal, there is a way to remove all these things. That's it. Because it is optimal, we, everything else can be removed. So can we find a condition where everything else can be removed in pairs? Okay, now let's just think about that. So we want to remove everything else in pairs, right? Let's say if some subtree, if all subtrees are less than or equals to this size, then I think it's possible. That's known. We can just choose different subtrees, right? If all subtrees are less than or equals to that value, if all so let's say the remaining things are total of total z things. If all of them are less than or equals to z by 2, that means no subtree is greater than everything else, then we can definitely remove that, right? If no subtree is greater than or equals to z by 2, then we can definitely remove that, right? I'm trying to find what is the smallest v for which we can remove everything. Okay, we are just trying to brute force that. Yeah, so we're trying to brute force on that line graph. Okay. Uh, if everything can be paired and removed, what does that mean? If all these sizes are less than or equals to z by 2, then we can surely do that, right? Then we can surely do that. But if this size, if one thinks one of the, how can we surely do that? Let's just claim that we have a group of things where none is entirely greater than the remaining everything. Okay, if it is exactly equals to the remaining thing, just pair. If it is more than remaining things, then let's just look at maximum. Then subtract that and subtract something, you still have maximum less than or equals to remaining other things satisfied. If there are two maximums, pick those two. So maximums will always, that thing will always be satisfied. But then if there are odd maximums, I mean, if everything is less than or equals to z by 2, just take that and then keep removing. I think that works somehow, that pairing works. It only doesn't work when one thing is greater than or equals to everything. Now what do you do? Now what do you do? Maybe you can just find the line graph of this thing and then try to see if that line graph is greater than or equals to everything else or not. Right? That means you can reduce the to till here. Right? So that seems we are trying to get some structure into the problem. We haven't solved it well, but then that's true, because you can make this alone. How much you can reduce that? You can keep removing, and then you can reduce that to this much, a line graph, right? But then if this line graph itself is greater than how z by 2, then it's impossible. Else it's possible. If that line graph itself is less than or equals to the whole remaining things. So first the subtree is greater than or equals to remaining things. And then what's the line graph that you can get? So this makes the problem at least solvable in O of n square or O of n cube, right? We can solve this in O of n too, but it's clarity good, because If I'm good looking, but the clarity makes me not good looking, that's not good, right? Where are we? So, at least this got some structure into the problem. Can we further simplify this? Let's just look at it, okay? Okay, but if this is having the greatest, if this is having the greatest, even those cases we can ignore. Why? Why? If this is having the greatest, we can ignore those cases. Why? Because after you shrink it to a line graph, before that itself, you can remove everything else, right? You can remove everything else. If this is the greatest, and then you can shrink it to a line graph, right? So now you can remove something, you can remove this, but then this will become a shorter thing. So if this is the shortest, there is no way that some other thing can become big thing. Is this fine, people? You're scaring me with that. Maybe test case 3 doesn't follow these leaves. Maybe then I'm wrong. 1, 2, 2 goes to 1, 3 goes to 2 goes to 1, 3 goes to 2, 4 goes to 3, 5 goes to 4. Till there it is 1, 2, 3, 4, 5. I see that. And then also 6 goes to 2 and 7 goes to 4. So what's the graph? 1, 2, 3, 4, 5. Also 6 goes to 2, 7 goes to 4. So now I just want to make sure that we are right. What's the answer? 2. 2 pairs is nothing but 7 minus 4, 3 being the longest length. Can we have 3 being the longest length? Yeah, we can have this thing. Right. And then this Z 3 greater than remaining. But this can be simplified further into a line graph 1, which is less than or equals to remaining. So all of them can be removed. So 3 is the minimum thing. Okay. So I'm back. So we can only care about this being maximum. Okay. Why? Because if something else is being maximum, that means probably this is not optimal anyway. Okay. Something else is being maximum, we can just ignore that. So if this is being maximum, now we have to again worry. It's too big. 2 goes to 1, 3 goes to 1. And then everything is going to 2. 1, 2, 3, 4, 5. 2, 3, 4, 5, 6. And then things are going to 4, and then things are going to 7. Oops. Did I have any messages? It's probably right, bro. It's probably right. 2, 3 goes to 1. Okay, 2, 3 goes to 1. We have 2, 3. Remember them. 4, 5, 6 goes to 2. 4, 5, 6 goes here. And then 7, 8, 9 goes to 4. 7, 8, 9 goes to 4. 10, 11, 12 goes to 7. 10, 11, 12 goes to 7. See my numbering. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now probably let's see if this is okay. Let's go back to the answer too. 5 is the answer. What does that mean? 5 pairings means 10. So 2, only 2 will be left out, is what they mean, right? So except these two, can you remove everything? We have only one here, but then this is being too big, right? But these things can be removed a lot of times. Maybe remove this, maybe remove this. Okay, maybe remove this, maybe remove this. Okay, maybe remove this two, maybe remove this two, maybe remove this two. So what's the stick graph you can make it? 1. If you can know that info, you can see if that is greater than or equals to remaining things or not. So we want things. We can cover everything by trying to see if nothing is greater than or equals to remaining things. Then that's a good V. That V is achievable. Okay. But if some of these things is greater than or equals to, you need not care about that way because that's not optimal anyway. But if this is being the greatest, then find the answer of small minimizing that, and then again you have your answer. So we can solve this now in O of n. I'm sorry if I don't know the difficulty of the problems and I'm complexing things unnecessarily. Can we simplify it a bit further? Probably no. So if none of them is greater than or equals to remaining, then done. This is a possible V. Okay. All such things are possible V's. But if this, if some other thing is greater, ignore that because that's not optimal anyway. Optimal is either above or above here. here or here. But if this is being greater than or equals to v, then it's still possible that this is optimal. Why? You can remove you can remove everything, but then you will keep few things. You will keep few things, but then go down. Okay, if you go a step down, what happens? Even in this case, if you go down, what happens? This size is greater than or equals to everything else, right? If you go down, the optimal length will increase. So don't go down. One minute, let me think again. After this question, I'm sleeping, guys. I won't solve C again. You guys can somehow figure out how to get P1, or else maybe something else, find something else in that and then solve it, because yeah, I may read, but then I won't solve this. I won't solve more. So for this, can we have the answer of this? If we have the answer of that below subtree, then we are done. Right. So so let's say for each subtree, can we find this answer using similar logic? Let's try to think of that. Okay. For this subtree, and then maybe can we go recursively? Let's think of that. For this subtree, we have all these subtrees, right? And now we want to find the answer for this subtree. Okay. So let's try to see what's the shortest line you can get by removing things from this. What's the shortest line you can get by removing things from this? What's the shortest line you can get by removing things from this? What's the shortest line you can get by removing things from this? Let's say you have these values. Okay. Now you want to know the answer. What's the shortest line you can get from removing all these things, right? Why am I coming here? Because it's somehow I'm coming here, okay? If because as you keep removing leaves from different things, you will finally left with one such a stick, right? So let's again do the same thing that we have been doing above. Let's do it just on this thing. Okay. If sizes of all of them are less than or equals to remaining sizes, then we can remove all of them. The answer is 0. Whatever the shit we have done on the complex thing, let's do that here. Because most of the times we do things recursively. If something has size greater than remaining, that will be only one thing, right? We know what it is. Only one thing has size greater than remaining things. Now, even if you keep everything aside, even if you try to help this thing by themselves, you have that length, you have that minimum length. If that length is, you tried helping it as much as possible, if that length is less than or equals to remaining, which means you can reduce this thing by 2 by 2 minus 2 minus 2 up to so on. everywhere from there to here, right? Everywhere from there to here you can come. Means maybe we have to be a bit more careful because we can only do -2 but not -1. But if this is greater than everything, you can keep reducing it to just one less, I think. When you get it to one less, it will still satisfy nothing is greater than the remaining things, right? Okay, -2 is also works. -2 also works, but then okay, now let's see, let's think of the problem again. If this stick is less than or equals to remaining, then what does that mean? You can make this big thing to this plus 2 plus 2 plus 2 everything until the long back, right? All these things are possible. So now this is less than or equals to means plus 2 is also possible. If this is less than or equals to plus 2 is also possible, that means we can somehow remove all of them. Probably. Because you can come till here, which is almost equals to all of them. And then you will come here. Now probably if you come here, that means you can come till here. I'm trying to be a bit more careful because we are only doing -2s, okay? But the problem seems to be solved almost. We have to be a bit more careful here. So let me be very clear. Let's rem be the remaining things. Okay. And now we have this as rem. We are here. Okay. We can only do -2. And then the remaining path is somehow less than here. You can go till there. So you can go from here to here, let's say. After going here, is it possible that remaining things will be greater than this again? See, if we can go 2 below, then we are good because if this is much smaller, then we are good because then we can just come till here and then we can solve the problem. Let me see 1 minute. So if you have this length as minimum m, that means you can have m plus 2, m plus 3, m plus 4 up to so on all the sizes, right? All the sizes are possible here. Okay. But then if this m is small than remaining things, then we can probably remove everything. But if that m is big, then how much can we remove? We will first make that m and then we keep removing all these things. So the m minus sizes of remaining would be the answer then. If that is greater than everything. If that is greater than everything, m minus sizes of everything is the answer. But if that is less than or equals to everything, then you keep remove outside and this, outside and this, outside and this, outside and this, and then you come here. Right. Let's say you're coming to just -1. If you can't match this just -1, then what happens? There will be only one thing here left out. That one thing says these things have even number of things, not odd number of things. For that reason, at least that much is possible. Because if the total number of things are even, at least this should be possible, right? You cannot make more than this. You cannot remove more than this. So that, see, my carefulness at -2 itself is leading me to this case. See, or else we could have just seen this case first, but then see my carefulness. So the problem is solved now. Okay, I will tell my solution again. Okay, so the point is, if something is greater than or equals to, if something is, if everything is less than or equals to remaining, then we can remove everything and keep only one thing that's left at the end. Okay, that's one basic thing we can say immediately, right? If everything is greater than or equals to other things, then we can make them as one final thing. We can keep removing. But if something is too big, we have to see its answer. If that answer is small, that means if that answer is also big, then that's the best we can do. We are keeping everything in their full power, but then we're simplifying that as much as possible. And then, and then we're trying to remove that. That seems the best, right? Because keeping this for late is good. Why? If you're using it right now, don't do that. Maybe use it later. Seems good, right? And then if this is greater, you will say if this can be greater or not. Okay. If none of them is greater than half of remaining, then see, this is a simple problem now. You can verify it's my same idea. Is the Ashmahota there? I need food. It's Sunday. Maybe I'll order Blinkit something, okay? I eat a lot of trash. Is Ashmahota there? No, I don't. You guys should do pull-ups, push-ups, everything. Ashmahota is not there. No, I sometimes go to gym. I sometimes go to some shitty group classes. There will be aunties working out there. No, those are not any good things. That's best. So, guys, is anyone following? Please answer. Now, bro, hear me out. Okay, hear this again. I'll tell it again. So, see, if all the things are less than or equals to other things, maybe we can just make them as one or zero. But if If something is greater than other things, then that is too big. If something is too big, then what you have to do, you have to, then I'm claiming that removing this with something else is bad, trying to remove them with them is good. Let's say you have two things getting paired with this and this leaf got removed with this two. Instead of that, you can just pair them and remove, right? So you will have outside things more. So that was the claim. And then you will be left with one leaf. So now if that leaf is again, so if the whole size is big, now remove as much as possible. Even if that is bigger than size of others, then you can't do anything. That's the greediest optimal thing we can do. See, here I came down to that, something being too big. And then again I'm coming down to that in this also. Fixing this or maybe trying to find for this. So how do I find? I need sizes of all, and then I'll see max size is greater than or equal to remaining or not. And then if it is less, I'll go to that vertex V that has the max size, which is greater than everything else. I'll find its answer, and then I'll check if that answer is greater than everything else. But then if that answer is not greater than, if that answer is greater than or equal to everyone, answer will be answer minus its remaining thing else. Otherwise, we have answer. I'm good. Simple DP. So see, now I'm showing solutions are simple. Clear proof. I have done clear proof. See, there are other people higher rated than me, but then they can't do such clear proofs. People just get rating by just solving, speed forcing some problems, speed forcing ABCD, and then get rating. You guys should judge me by seeing my skills, seeing my logic, seeing my muscles, and not. See, the input is just a tree, and still we have a nice problem. It's a good problem. See my implementation skills too. I want size of the below subtree, right? I'll just maintain that too. And I want, uh is it like a strongest right length? What should we call? Should we call it DP? I don't see. DP is famous because people can't name things. That's the reason why DP exists. And then you guys get scared of DP. I think DP only exists because people can't name things. I like this, childs. So these are good directed edges. So we can only add this to. Okay. We only want size. Void DFS of int v int p. B of v equals to 1 for int u edge of v if u not equals to p. DFS of u comma v. B of p plus equals to b of u. Okay. So now after finding all the answers of below things, what do we want? What do we want? Okay, what do we want? I want remaining things. I want this vertex V with maximum size. So I will find max. I will find sum among all these sub childrens, right? If there is no children at all, let me add those stem too. Okay, there is no P at all. It's a good DP. If adj of v dot empty of, then dp of v is just 1. You can't do anything. It's child. B of v is already set to 1. return. Else we have maximum. Let's say maximum size b of adjoint of v of 0. Okay. So I want maximum, I want some to know what are the remaining things to, right? M should come first. I should become at least grandmaster before flexing like I am flexing. I know that. I know. Let me also have max mu. Oh, my nail. I have many issues in general, but I don't care somehow. Wait, which is computed first? I think this is computed first. Maybe. Then it works. So we have some, we have max index 2. If sum minus m greater than or equals to m, that means max is not greater than everything else. That means dp of v equals to b of v remainder 1, remainder 2. Else m is much bigger, right? Now if dp of mu, from there how many things can be left? If this shit is greater than or equals to sum minus m, which is remaining, still, okay, if remaining is again greater than or equals to this, okay, let me write it in a nicer way. If again remaining is greater than or equals to dp of u, what does that mean? You can again remove shit. dp of mu. So dp of v is again b of v remainder 2. But if you can't do this, then this dp of v itself is too big. And then, so I have thought a lot, but then everyone will try. Can they find the answer recursively, right? Everyone will try. Can they find the answer recursively? Okay. What's the way of find? I think I have overcomplicated the problem. I thought the problem is difficult, but then if everyone tries, okay, try to find the problem recursively, then it seems obvious that okay, if something is not too big, you can remove everything. Is that obvious? Maybe after finding leaves, right? Maybe after finding the conversion into leaves, maybe. Now, if something is too big, try to reduce that. If you can't reduce that too much, then you cannot reduce that too much. dp of v equals to 1 plus dp of u. 1 plus dp of u minus remaining things, sum minus m. dp of 1 will always hold parity with this thing. See, parity holding. Even here it holds. 1 plus, it holds. Parity of this equals to parity of size of b. These are just size of b. This is just size of b of b. You can't pair this at all, right? You guys may think I'm talking shit. I was talking shit, but then if the problem is right, you guys can do. I mean, I unnecessarily came from wrong direction, but then this seems too obvious, right? This seems too obvious because trying to find for one subtree is always things people do. I over expected the problem. I thought, okay, trying to find for one subtree is maybe not possible. That's why I will try to look at in some weird way. I thought, but then trying to find something for one subtree is always true, right? I'll sleep. I can't waste my Sundays on these stupid streams where no one watches them. Okay, just 95 milliseconds. Let me read E. See, this is also just DFS logic, and then you guys people will say topics. What are the topics I should learn? What are the topics that will make you remember that okay, if something is not greater than everything else, you can pair fucking them up? What are the topics will tell you that? Like you have to be able to use such simple logic sometimes, right? Not simple logic. It's like see, you have to realize that you can do simple things, and then you have to work on doing those simple things better. But then you guys don't do that. You guys think, okay, there are some complex things that I cannot do, so I won't do anything. Everything is simple, but we can do simple things. So we have to increase that skill of little bit trying harder, little bit trying to see something, trying to say something. Okay, we got hi dude from Sai. Hi. Like the video, guys. Sai, if you haven't liked the video, like the video. So where am I? I'll read E because I told I will read E. You're given a length and subsequence of non-negative integers for k equals to 1 up to 1 and solve the following problem. See, this was where I overestimated the problem. I overestimated the problem. Otherwise, trying to find one subtree is obvious, right? I should have started there. I was trying to find overcomplicated, and then I came down to only subtree matters, and then I came down to I should have just seen if subtree works. For each subtree, if you can find using below things, then the answer is done. Then it's too simple. Okay, if all things are small, the weird logic that I was trying to use here, if it was contest, I would have done that. I think the weird logic that I was trying to use here, I could have just used that on subtrees and then done. This is too big. Here I was thinking that if one is too big, what should I do? That I've solved the problem here itself, and then the same thing has been used here. So this proves that we don't get solutions randomly. We do the work that we have to do, looking at the optimal. What can we say? We do that necessary work. And then that necessary work itself solves the problem most of the times. You guys don't do the necessary work, and then you guys think that's a great idea that you don't know. You're given a length and subsequence of non-negative integers, yay. K equals to 1, solve the following problem. For all of them, we have to solve the problem. That means that it's not that difficult of a problem. Like, not that difficult to even work a bit. It may be difficult to solve the problem entirely, but then because it has to be solved for everything, and then there is a simple proof, right? See how I have even showed simple proof to this. You guys should realize where my golden rules comes from. My golden rules comes from the fact that we make the complex problem seeming to have so many things into something that's so small and so simple code. Codes cannot be too complex. Code you cannot do n factorial operations. Code you cannot do so many things. That means you're doing something small. Finally, from there to there, if you are going, that means solutions are simple. And code, if it is correct, if it is passing all the test cases, that means there is a proof to probably that, otherwise they wouldn't give us the problem that this code is that. It makes sense that okay, you have simplified everything, and then now this implies the problem. So that means there should be a simple proof too. And implementations should be simple if you make things right. Because see, how much did I struggle to implement this problem? How much did I struggle? Is this struggle? No, right? Let me read it. Find the product. That doesn't seem that good. Modulo of AI, all integers between 1 and k, inclusive such that product problem. Bitwise order of AI and AK equals AK. So we have a list of integers and what the fuck they want. For each k, we want product of all the numbers whose bitwise or is AK. So this seems like a subset thing, right? A bit. Would something like a subset DP work? I don't know, but we have to see. We want product of all of them. See, product doesn't mean much. Product just means you must somehow group them. You must somehow get the group. Product says that. Product means you somehow group them, you somehow do multiply one after the other, because you cannot have something nicer in terms of product, right? You cannot have a nice logic in that, but then you have to group them somehow. Like, for the answer of this, you must do maximum, you must somehow find product of all of those things, right? How big is 2 power 20? It's not too big. I mean, this is what we have to use. If it is 2 power 64, the problem is unsolvable. If because it's 2 power 20, we have to use this for sure. Right. Now, is it like subset mask kind of DP? Because AK is just a mask, and then you want to cover the whole subset that's inside this subset, right? Inside this K, whatever the subsets of this AK. If you see AK in bitwise representation, all of its subsets, all of the subsets product is what you want, right? So you want subsets product. When you have some AK, you want subsets product, and then you should be able to update this somehow data structure or set you are maintaining into increase the product of some bit mask, right? Let's say you have uh, for each bit masks of 2 power k, you have, let's say you have the tree itself, you have that big tree itself, okay, of subset mask tree. Somehow you have that tree. Now what do you have to do on this tree? It's not a tree, but then maybe there are some ways to make it a tree. Maybe there are some other, maybe subset some has a tree, I think. So if you have a way to get product of all the subsets, then if you have a way to get product of all the subsets, then you can just update k with ak with ak's value product, and then you'll again query product of subsets of something later. So that's what we must do to solve this problem. That's what we must do. So after making some statements, now we can go a bit deeper. When solving problems, you don't solve the entire problem at once. You make one statement, you make one valid statement, and then you try to go further a bit more into that after that. Okay, I'm sleeping. Good luck, guys. We are not able to do C, but then we did A, B, D. So I think we can see. So I think we can skip C, right? My guy is never leaving queue method. Nice. Good luck. I'm leaving. Update and then get subset somehow. I think there is subset some DP, SOS DP that is there where we try to maintain. I never solved it on my own. If you don't solve it on your own, we can't remember that. If you solve it on your own entirely, then you will remember that very well. Like the video, if none of you have done. So doing things on your own is very important to remember things. Okay. Also subscribe to my YouTube channel because we need 986. We are approaching 1,000. We need 1,000. This thumbnail, I chosen that thumbnail because it gave me a chance to take a photo. So that thumbnail was chosen by me. Bye. Oh, Yashmota finally came to just say goodbye. I hope he was there when I solved D, but then you can check the D part, Ashmota. Okay. Trying to solve just for one subtree was enough somehow. Trying to solve just for one subtree was enough. See, when there are cases, okay, in this case it's done. In the remaining case, what? If you don't do what you can do by telling, in this case it's done, you cannot go there most of the times. Okay, the problem won't be solved all of a sudden, even if it has just one if else. No, I don't think it is wrong. It can be right. Maybe it's correct. Maybe it does the same thing. Whole video tomorrow. Damn. Nice. Skip wherever you can. Try to understand D. Seeing the whole seems like a bigger. Hey! I got scared on camera. There's a dog. There's a collared dog that came. That's just survival instincts. Okay. That's not getting scared. Right. I can be the dog. Right. I can be the dog. There's a dog in me too. Right. Good night.